Hello everybody, welcome to my video. This video is second in my series on Udacity self-driving car nanodegree projects. So in the first video we saw um, um, my work on a project called Kidnap Vehicle, which dealt with implementation of a particle filter, two-dimensional particle filter in C++. And this video is going to deal with concept known as extended Kalman filter, and the objective of the exercise is um, to track a bicycle which is going around a self-driving car. But it could essentially be used to track any object, another car, pedestrian, bicycle, which is going around the car. This project name is Extended Kalman Filter, but we'll go through the concepts, what's a Kalman filter, what's extended Kalman filter and all that, see the execution. So let's get started. So first off, I want to, I'm going to minimize here. I want to go through the concepts of Kalman filters. It won't be a very exhaustive explanation. I would recommend people wanting to know more about Kalman filters in detail. They refer to videos on YouTube. There are excellent videos from a professor. I don't want to butcher his name, but I think his name is Michael Van Biezen. Those videos are from iLecture Online. They are like 40 videos. They do a very good job of explaining the Kalman filters. But what I'm going to do is do a summary explanation, which is more relevant to our project here. What's a Kalman filter? Now, Kalman filter is used in more common applications than we can imagine. So, for example, Kalman filters is used in thermometer in coming up with a accurate temperature estimate. But in our case, we are going to look at Kalman filters which are going to measure or come up with ground truth position for like a self-driving car, or in this case bicycle around the car. It could also be used, for example, to track satellites or airplanes. So many applications in higher dimensions. I guess if it's a satellite or airplane, it would be higher dimension. For our bicycle, it would be two-dimensional. So it's used to track. It's used to come up with an accurate estimate of where the object is. So what it does is this is a flow chart. So what we do is we come up with a error in estimate first. We come up with the original error estimate, and we pass it, and then we come up with error in data. We pass it to calculate something known as Kalman gain. We'll see more, and then we'll pass it to a function to calculate the new current estimate. In this function, we are feeding the previous estimate, which for the first time it will be the original estimate. And as our data input, the measurements are coming in, and then we update the estimate, and then we calculate the new error. We feed it back over here to calculate the Kalman gain. This current estimate gets fed back to the previous estimate. So it's an iterative process. So it's an iterative set of mathematical equations which uses prediction and update in sort of a loop. That's how it converges to the actual ground truth value. So if the error in measurement is higher, then this function will give more weightage to our estimate. we'll see some equations that will probably make more sense. And if the error is low, then it will give more weightage to the measurement. So this is just a general idea, general flow. We'll get more into details. I just wanted to give a summary idea first. So now want to go through some equations here. We saw a flow chart. So the equations here let's see, gonna minimize that. So first step, like you saw, was to calculate the Kalman gain. So Kalman gain is error over estimate divided by error over estimate plus error over measurement. Then that's fed to calculation of the current estimate. Current estimate is previous estimate plus Kalman gain times measurement minus previous estimate. And then estimated time t is over here 1 minus Kalman gain previous estimate. And then this estimate is fed into again Kalman gain, so it goes into a loop, predict, update, and it converges to the ground truth value. Very summarized idea of what a Kalman filter is. Now this is a Kalman filter. This project obviously is called extended Kalman filter, and we'll get more into it. But the extended Kalman filter deals with non-linear or more complex motion models, like for example a bicycle going around like this in around your self-driving car, not linear motion. So that's what extended Kalman filter is. So now let's see how does I want to take a segue here and show how the let's see here. I'm gonna pause 1 second. Okay, we are back. Hopefully that pause worked. So I want to show how this project when done would look like. This is a video clip from the course itself, the self-driving course. So I'm gonna play it. This is my self-driving car. There are Lidar and radar measurements. So Lidar measurements are the red circles, radar measurements are the blue circles, and then the green were our estimations. And then you see the root mean squared is within the range. So basically it's able to estimate based on Lidar and radar measurements to come up with accurate estimate. And so this essentially is also an exercise in sensor fusion, because you have Lidar, you have radar. Now Kalman filter can be used just for sequential measurements from Lidar, for example, but here we are going to use both Lidar and radar measurements. The main difference between Lidar and radar, there are many differences, but radar is able to measure the velocity. Lidar just measures the position. It doesn't directly measure the velocity. And for radar, the spatial resolution is less. For Lidar, it's more. There are more differences, and we'll go through some as we go through the course here or through the video. So going back to the equations here, let's see. So we were saying, so for the two-dimensional, which exercise here, we pass the initial state. So initial state is x0, p0. So x0 could be just px, vx. So position in x dimension and velocity in x dimension, or it could be px, py, vx, vy for x and y dimensions, or it could be px, py, pz, vx, vy, vz for x, y, z, for example, an airplane. P0 is the process is the covariance matrix. So that's essentially a covariance matrix will have on the diagonal it will have the variance for example sigma px square, sigma vx square, like here, and then on the off diagonal it will have the covariance, so sigma px, sigma vx on the off diagonal. So this initial state first fed to it's first time, so that becomes the previous state. Then we predict using this function here, so we predict our new state, our new error, and then we pass it to calculate Kalman gain. Our new measurement comes in here, and then we calculate the new error, we pass it back. So this is again predict, update, calculate the Kalman gain, new measurements come in, then the new error goes back to calculate the go back into the loop, and and at each time step the updated state, meaning the updated state, meaning position and velocity, and the updated error is output. Let's see another picture here that's uses some different conventions here. So this is prediction, this is update. So I guess we'll go through it in a different way. I'm just gonna not go into it at this time step here. So let's go through some more concepts for Kalman filter or extended Kalman filter exercise here. So you see over here we have, like I said, it's also an exercise in sensor fusion. So we have Lidar data, we have radar data. Measurement comes in. First you initialize the state and covariance matrix. So your state is position and velocity in x, y dimension, let's say, and covariance is like I said, variance on the diagonals and then covariance on the off diagonal. Then we predict based on the functions that we saw and we'll see more of. Then if it's a laser matrix, then there's another one way of doing it. If there's a radar matrix, there's another way of doing it. If it's a laser measurement, we use another matrix. If it's a radar, we use another matrix, and then we update, and again the same loop keeps on going on. So let's see here. So again, Kalman filter, again, the concept is predict, update. So let's say we predict at time step k plus 1. So this is your original state and original covariance. This is prediction of xk plus 1 given at k and pk plus 1 at k. Then let's say a measurement update came in from Lidar, so we update it, and then we predict again. Then a measurement update came up with from radar, and then we predict again. And then if it comes together at any time step, Lidar and radar measurements, then we still go predict, update, predict, update at the same time step. So we still do predict twice. First we could go with Lidar or update with radar, and then second again. I mean, if we did Lidar first update, then we do radar second update. So that's general intuition here. So let's go to some of the equations here. So to predict, let's go back to the equations here. So the new state is fx plus new. Now new state here, the f is, so x this dash here, or it's x predicted, is fx plus u. Now f is a state transformation matrix which will be if you have if we have only px and vx, it would be 1 dt 0 1. And if you have px and py and vx vy, then it would be one it would be 4 by 4 matrix with 1 0 dt 0 0 1 0 dt 0 0 1 0 0 0 0 1. And so now this new is the noise, this u function here, and then so this p dash or predicted covariance is again this f is state transformation matrix. So this f is just used to be so that this new prediction is in the same dimensions as the old prediction. So therefore this is just for matrix manipulation that we use this state transformation matrix f here and f transpose here. And now q is the process noise covariance matrix, which we'll get more into. So this is the prediction function. Let's go back here. So like I was saying, fx plus bu plus v or nu. So this is x is predicted, f is the state transformation matrix, bu we are gonna ignore for now because this is when we are considering acceleration. So we are going to consider new, we're going to assume constant velocity and therefore no acceleration, and we are gonna in fact also not take new, this noise here. We are going to consider noise in this function here. We're going to consider the noise in this q function here. So we're not going to take this noise. We're going to accommodate or account for the noise in this q function here, or q parameter I should say. So that's that. I'm just going through the equations so that it makes more sense. So like I was saying, f, if it's just one dimension, the state transformation matrix would be 1 dt 0 1. And this z is our measurement. So so we are now coming into measurement. So z is the measurement. So we are so again it's a loop of prediction and update. So we are predicting the state and the error, and we are measuring. Meanwhile the measurements are coming in. So this is measurement z. So going back to some of the equations here, this would probably make more sense. Let's see here. Let's try to make sense of it. So Kalman gain is error of estimate divided by error of estimate plus measurement. So if I correlate these equations with the two-dimensional equations here, Kalman gain will be error of estimate is p, and then so this will be p divided by p plus r. R is my error of measurement, and error of estimate is p. So Kalman gain is p divided by p plus r. Now the only thing is for matrix manipulation we do it as let me see if I can write it down. I'm gonna try writing it down here. Let's see. So Kalman gain equals to error of estimate divided by error of estimate plus error, sorry it's not very legible, but error of estimate divided by error of estimate plus error of measurement. Now for my two-dimensional matrix model where I'm using matrices, so this will be error of estimate is p, error of estimate again is p, and error of measurement is r. Now, for matrix manipulation, we are using a measurement matrix. This is just for matrix manipulation, so that now we're going to use a matrix known as H. It's called measurement matrix, and we're going to use H transpose. So this is just so that uh, the coordinates of Kalman gain, or the dimensions, I should say, um, um, are uh, are what's expected. So this is just used for matrix manipulations. H is called measurement matrix. For example, uh, like for Lidar, we are measuring, uh, we are predicting uh, position and velocity, but we are measuring only position. So to transform our measurement space into prediction space, these matrices are used. So this H matrices. So Kalman gain, that was the equation for Kalman gain. So now while we are at it, let's go through equation. So what's done here is this thing here for matrix manipulation, H transpose plus R is called as S. Okay, so Kalman gain is now PHS inverse. So let's go back, and that's what it should say here, not this one, but so Kalman gain, if you see, is PH transpose S inverse. So sorry, it should have been H transpose. This one should have been H transpose. So we called PH transpose plus R as S. So Kalman gain will be PH transpose. So Kalman gain will be P H transpose S inverse. Okay, so that's Kalman gain. So that takes care of that one equation. Now y is z minus hx. Okay, so this function here, measurement minus estimate t minus 1. So measurement is z, estimate time t minus 1 is x bar rather, xp I should say, and then h function is used to again matrix manipulation. So let me write this. So I wrote the equation for Kalman gain first. Where did I write? Kalman gain is P H transpose S inverse. And then let me write the equation for estimate at time t. So estimate at time t, estimate time t minus 1 plus kg measurement. So z, sorry, just thinking here, 1 second. Come back here. Y equals to z minus hx. So where was it? Z minus hx. So this thing here, okay, I got it. So this is xp or x bar rather. So let's go back to our snip here. Let's see if I can or let's just write here x, this thing equals to previous position plus Kalman gain times z minus hx. I think so. So z is measurement, h is estimate, estimate at time t minus 1, and h is measurement matrix. So now this whole thing is called y, right? So x equals to x plus ky. I hope I have it right. Let me see here. Rather here, x equals to x. Okay, so that's wonderful. So we took care for actually first equation, second equation, third equation, fourth equation, and now the new error. Let's see here. New error. Sorry, I'm trying to get to this one. So new error is 1 minus Kalman gain error at time step t. So going back to the snip, so new error p will be equal to, sorry, just thinking here, over here. So new error is I minus kh, so kh previous error. So go back here to my snipping. So so we have one equation is this, one equation is this. So this is Kalman gain, this is new estimate, and new error estimate is p equals to I, which is my identity matrix, corresponds to 1, kh, h again is measurement matrix, p. So I think this is wonderful. We have 3 update equations. So Kalman gain was error of estimate divided by error of estimate plus error of measurement. So we got this equation. Now this equation corresponds to new estimate at time t equals to estimate of time t minus 1 plus Kalman gain measurement minus estimate of time t minus 1. So this equation corresponds to this. Now this equation, the new error, I wish it was more elegant, but new error is, let's see, new error estimate of time, error of, error estimate at time t equals to 1 minus k error estimate at time t minus 1. So this corresponds to this, see, 1 I minus kh. So we have 3 equations for our update. So I'm glad we got that, even though it wasn't very elegant. So now let's save this just for. Okay, so now let's let's write the prediction equations again over here maybe. So prediction equation. So prediction equation, the new state is fx plus new. New is noise. It could be actually fx plus bu plus new, and new is noise. B, actually this whole thing is when you have acceleration, but we are considering no acceleration, constant velocity, and we're going to account for noise in our this function. And this is error of measurement, error of estimate plus error of measurement. So new error is, or predicted error is, no, sorry, I take it back. This is the predicted error is old error plus process noise covariance matrix, and we haven't looked at this term yet. This is another manipulation. This is another Pandora box, if you will. So these are the 2 equations for prediction. We saw just a little while earlier the update equation. These are the prediction equations. Okay, wonderful. All right, and go back here one second. So F, as I was saying, is a state transformation matrix which will be 1 dt 0 0, or 1 dt 0 1 if your x is let's say px vx. Okay, but no dot here, just x state. If your x is px, py, vx, vy, so that means two-dimensional. Then your f will be, so then your f will be 1, 0 dt, dt is your time step, 0, 1, oh, I'm sorry, I don't think I have it right. 1, 1, yeah, 1, 1, 1 dt, 0, 0, 0, 0, 0, 0. So that will be your state transformation matrix if it's two-dimensional. Q again we have to see. All right, wonderful. And then Z matrix is this. It's actually if there's no, if then it's not, Z is the new, so Hx plus W. Again, W is another noise. And so the velocity is constant here, so Z is P dash. Okay, so now let's go to next function here, or next, let me move my picture here. Okay, I think we've covered a few things here. So we talked about this. So this is state matrix if we have two dimensions, px, py, vx, vy. So p and x and y. So this is f, and then so now this noise which we are going to ignore actually. It could be written as nu for px, py, nu, and nu of vx, vy, because there's noise for position of x, position of y, vx, vy. And like I said, if we are going to account for this noise in our Q, how we come up with Q, which is the process noise covariance matrix. Okay, now Q, which is again, so like I was saying, to calculate our new error, this is our old error, not to predict our new error, it's an old error plus this process noise covariance matrix. And F, like I said, is state transformation matrix, just to come up with the right dimension. So Q is GQV G transpose. Now what's Q? First of all, what's QV? QV, or Q nu I should say, is sigma ax square, sigma ay square, sigma ax ay, sigma ay. So acceleration noise x y in the diagonal, and then off diagonal the covariance, and off diagonal, so since there won't be a correlation between sigma ax and sigma ay, so it will be 0. So Q nu is sigma ax square, sigma ay square in the diagonal, 0, 0 and off diagonal. Now G is nu, so the nu from previous, our state prediction was written as nu px, nu py, nu vx, nu vy, is half delta t square ax. So because a state, because a new state is old state, so px is px at time t minus 1 plus v delta t plus half ax delta t square. So since, like I was saying, we didn't take nu over there, we are accounting for all that in the process noise covariance matrix. So nu is this matrix here, and then v new velocity will be ax, old velocity plus ax delta t. So then this nu, we are writing this thing here, we are writing it as here, we are taking out ax, ay. So G is this matrix. So our Q is G, which is this matrix here, Q nu, which is this matrix here, and G transpose. So that's what process noise covariance matrix is. Okay, wonderful. Let's see here. H, like I was saying here, in our some of the diagrams that we drew, I think we lost that first diagram. H is the matrix which is used for, in fact, I could use this to show you. H here is the matrix which is used for measurement transformation. And like I said, because for LiDAR, like you're only measuring position, but in your prediction you have px, py, vx, vy, but in your update you have only px, vy. So it's just used for matrix manipulation transformation. So it's called measurement matrix. All right. Sorry, I have to go through it this way. Now R is the measurement noise. Where was R in our equations? R was over here. This is the measurement noise. And R is sigma px square, sigma py square, 0, 0 in the off diagonal. And F is this Q, after all that G, Q nu, G transpose, it comes out to this. All right, going to next. Okay, nothing to show here. All right, radar measurements. So for radar measurements, I think we want to talk about how radar measurements, we need to talk about radar measurements a little bit here. So let's look at this diagram. So this is vehicle coordinates. So wherever the vehicle is heading, that's x direction, this is y direction. So LiDAR is measuring in vehicle coordinates or Cartesian coordinates. Radar is measuring in polar coordinates. So over here, so this is your vehicle, okay, this is your pedestrian, and then so at this point, this is the pedestrian velocity in vx, x dimension, this is in y dimension, this is the velocity. So so the distance from the vehicle to the pedestrian is called rho. It's also called range. This angle is called phi. It's also called bearing. And then this is rho dots. It's radial velocity. So the radar, while LiDAR measures px, py, radar measures rho, phi, and rho dot. So that is crucial. So now h of x, which is the measurement matrix or measurement function for radar, will be rho, phi, rho dot, which converts to square root of px square plus vy square, arctan. Phi is arctan py divided by px, and then rho dot is px vx plus py divided by. So y equals to z. So this equation here, this equation y equals to z minus hx for extended Kalman filter. Yeah. So extended Kalman filter we are using for update of the radar measurements. So there is predict, there's update, there's predict, there's update for LiDAR and radar respectively. For predict, we are using linear model for both LiDAR and radar. For update, we are using linear model for LiDAR, but non-linear model for radar because of non-linear. So this h here, this h, this becomes h of x, which is nothing but this matrix that we saw here, because of rho, phi, and rho dot, the measurement in polar coordinates. All right. Now, okay. So there's one more very important thing here. So okay. So this x prediction fx plus u is also supposed to change if your prediction was also non-linear, but over here prediction is linear, so this is not going to change. Only this changed so far, where we said h instead of y equal to z minus hx p, we're going to have y equal to z minus hx. That function which was, we said, was rho phi rho dot. We just saw that actually. This function here. Okay, good. So now the another change is this this H matrix here, which is used in S, K, and P. This H matrix that needs to be transformed to a for our non-linear model, and that is done using so the linear model is converted to non-linear model through Taylor series approximation, which is I won't be able to get into much detail here, but it is this formula here. So this is first derivative, this is second derivative. So we are only going to consider the first derivative, and first derivative is called Jacobian matrix. Second derivative is called Hessian matrix. We're not going to get into second derivative. We will only consider the first derivative. So the Jacobian matrix. So let me reiterate this: H in S calculation, K calculation, and P calculation becomes Hj, which is your Jacobian matrix. All right. Cool. So Jacobian matrix. Let's see Jacobian matrix. Is it works out to this. So this is partial derivative with respect to px, py, vx, vy, which is in Cartesian coordinate system. Partial derivative of rho, phi, and rho dot. So range, bearing, and radial velocity. So rho was your distance, like that, from your car to the bicycle, and then phi was that angle. So this was rho right here, this was phi, and this rho dot was velocity, radial velocity. Wonderful. So that's your Jacobian matrix. These partial derivatives work out to this here, which we're not going to get into. Okay, so nearing the end of the concepts here. Talked about okay, and I think that's about it in terms of the. Okay, so we already, so like I was saying, if we go back here, okay, so we're going to toggle between this and this. So F matrix will be replaced by Fj, which we are not going to do because our prediction is also linear. H matrix in the Kalman filter, for extended Kalman filter, this in S, K, and P calculation replaced by Jacobian matrix. And to calculate your sorry, where was it? Y, we use, instead of H, we use Hx function, which was rho phi rho dot, and then rho calculated to underscore rho px square plus py square. Phi was arctan py divided by px, and then similarly for rho dot. Wonderful. I think so. This is here Hx, right? Exactly. And then one more thing, I think. That we needed to normalize phi so that its angle is between minus pi and plus pi. Okay, this is all in terms of concepts.
So here is my overall.
Okay, wonderful. So this was all in terms of concepts. We are going to talk a little bit about what the project required us to do. The project required us to update, program this in C++, and we needed to update write the equations in this Kalman filter.cpp file for the equation that we just saw. And if I can pull it, let's see here, these equations that we just saw. So if you see, x predicted is fx plus u. So like I said, we knew, and like I said, we ignored nu in prediction of state because we are going to account for nu in the Q. And so P predicted, what was it? Predicted error was this function here. So like that. So this is predict, and update is these set of equations here. Exactly same. Y equals to z minus h of x. and then S is HP, H transpose plus R. Kalman gain is P, H transpose S inverse, like that. And the new state is X equals to X plus KY, and new error is I minus KHP. So wonderful. That was all. Predict, update. That was the core exercise. This eigen dense library was used for matrix functions. Then this Kalman filter.h, you declare the functions here and the Kalman filter class. Then you have main.cpp file, which was reading the measurements. So for measurements, if you wanted to download it, I mean, do it in your system. I used Udacity workspace, but if you could download the measurements file and have it read. But this was being done by the simulator. So like I said, for this file, if you see, actually, let's go back to this file here and let me read my notes 1 second here. Okay, so yeah, for radar data, you had rho, phi, rho dot measured, and then in terms of ground truth, you had x, v, px, py, vx, vy, and yaw, which we ignored. And for lidar data, we had px, py measured. And then for ground truth, we had px, py, vx, vy, and yaw, which was ignored, yaw and yaw rate. So essentially, the difference was for this L rows with L as the first column. We had in terms of measurement, we had px, py. For rows with R as first column, in terms of measurement, we had rho, phi, and rho dot. Wonderful. All right. So this is this was the concepts here. Okay, so going back to the program a little bit more. So we had the main.cpp file, which was communicating with the simulator and reading the data and calling the functions. Then this fusion.ekf important file, where we initialized the variables and the matrices. So let's see, all the like P, H laser, HJ, F, and the noises. Let's see here. And then we calculated, in fact, Q here also. Process noise covariance matrix, which we saw was G, Q nu, G transpose, and Q nu was sigma x square, sigma y square, and G was, I think we saw that. Anywho, so yeah, so those were the, I'm going through the program in a very very high level right now. So basically the variables and the matrices were initialized in Fusion EKF. See, the matrices are initialized, the values are initialized for measurement error, for your measurement matrix, for your state transformation matrix, and then like state transformation matrix, you're substituting dt, and then you have noise a sigma x square, sigma ay square, and then you're calculating q because it needs sigma x square. Tools.cpp, you were calculating the Jacobian at j, which we saw. At j we saw here. That was for extended Kalman filter for sk, and it used first order derivatives of rho, phi, rho dot with respect to px, py, vx, vy. So, and then it also had a function to calculate the root mean square error between the ground truth and the estimates. So that's all actually in terms of the concepts and a very high level view of the program. What I'm going to try to do is run the program and see. So it requires GPU. I'm going to enable the GPU. I'm going to run the program and finish this video. So this is my second video in this series. I may, if I get around to it, I may record some more videos on the other projects. Not sure at this point. Leave any comments for in the comment section, and you can also see my write-ups at medium.com. Sorry, apologize. Okay, I'm going to move my picture here. I'm going to launch the simulator. Right here. 65480. So this is the extended Kalman filter project. Select data set to 1. Start. So if you see, it's just like I was saying, blue and red for Lidar and radar, and then green for the estimations, and root mean squared error is within range. So you can also see my write-ups, like I was saying, at medium.com at Manish Johari, spelled Jauhari Manish, right here. And leave any comments. Thank you for watching. Hopefully it was helpful. I'm gonna stop the video now.